Good morning, everyone, and welcome to this webinar where we will focus today on the topic of printed capacitive touch sensors. We will be your hosts for the next 30 minutes.
Hello, good morning. My name is Henrik. I've been working at Megaprint as a development and project engineer for 10 years. I have a background with an engineering degree from Aalborg University.
And my name is Anders. I've been working with printed electronics for the better part of 8 years now, in the role as key account manager here at Megaprint. Some practical information before we start. At the end, we will finish off with a short Q&A session. So in case you have any questions during the webinar, you're very welcome to type them into the Q&A module up in the right corner, and then we'll try to cover them all at the end. You're also welcome, of course, at any time to reach out to either Henrik or myself. Our contact information is displayed on the slides here. After the webinar, you will also be receiving a link to a recorded version, so you can always go back in case you missed anything, or if you would like to share it internally with any of your colleagues. So here's the agenda for today. We'll start by adding a little bit context to the technology and define the focus of the webinar, before Henrik will go a little bit more into the technical side of printed capacitive touch sensors. So as a technology, capacitive touch sensors have developed to become a very widespread user interface technology in the world of consumer electronics, as well as in some industrial applications. However, if you look at capacitive touch in general, it is not necessarily a new technology. So I was recently visiting one of our customers, and I believe they developed capacitive touch and brought it into the market in their appliances already back in the 70s. But back then, the capacitive touch came in the form of physical metal buttons, whereas consumer user interfaces today, they tend to be a little bit more smooth and minimalistic and stripped of physical details such as physical buttons. Most people associate touch interfaces with smartphones and tablets, and we call that kind of capacitive touch sensor for an on-screen sensor. Because it sits in front of a display, the optical requirements for an on-screen touch sensor is very strict, and therefore they need to be produced and bonded in a controlled clean room environment. However, many products cannot carry the cost of such a kind of very cost-intensive on-screen touch solution. So a little bit in contrast to the on-screen touch sensors, in this webinar we will be focusing on what we term as off-screen touch sensors, similar to what you can see in the pictures on this slide. So with this technology, you are still able to achieve a modern user interface with a broad contemporary consumer appeal, but at a much lower cost. So Henrik will come a little bit back to this later, but these would be sensors that are typically printed on flexible substrates like PET. They are typically using inks like silver, or carbon, or PDOT, from which it is possible to create either opaque or backlighted single buttons, sliders, turn wheels, or whatever other button technology would be required. So next we'll zoom a little bit in on some of the advantages of the technology and identify some of the market segments where it's widely used. So there's of course always pros and cons when making a design decision, but we've tried to list some of the general advantages of using capacitive touch sensors in a given application. And if we should highlight just a few of them, then we have already touched a little bit on the first one, but capacitive touch technology gives you the opportunity to design a modern and minimalistic user interface. This kind of technology is very easily customized in shape and layout to match the specific application. And it's very intuitive from a user experience perspective because it resembles what we all know from tablets and smartphones in our daily lives. Another advantage that I would like to highlight is that it's a very durable technology. So it typically sits behind some kind of front cover, could be a glass or it could be an acrylic front plate, but normally it always sits behind some kind of front panel. And because it does that, there's hardly any mechanical wear of the sensors. And it's also not directly exposed to detergents from cleaning, so it makes it a very durable technology. And lastly, from, you can say, the manufacturing point of view, this is a very scalable technology. Because the sensors are normally printed on flexible materials, it is possible to produce them by using high volume roll-to-roll production, which ensures a very high production efficiency. And at the same time, because you can roll the sensors up together and they don't take a lot of space, you can pack thousands of the sensors into a limited space and very easy to ship them around the world. So global logistics made very easy with this technology. And then in continuation of the different advantages, the technology is, as mentioned, very popular, both in, if you look at consumer electronic market segments, such as major appliances, HVAC and automotive, but it's also very popular in segments that rely more on intuitive and easy to clean user interfaces like medical devices. And then we also see it to be very popular in segments where the user interface is exposed to the eyes of consumers, which could be in the industrial control and automation market. So a very widespread use of the technology, you can say, into many different kind of market segments. Perfect. So with this, I'll just hand it over to Henrik for him to go a little bit deeper on the technical side.
Thank you, Anders. So a typical touch foil is used as an integrated component in a stack-up shown as in the picture you can see here on the screen now. So there are typically four main components. So as it was said before, we need a front panel, typically made of material like glass or plastic, the touch foil itself, a light well, and a PCB with the touch controller on it. And if we take a closer look at the touch foil itself, there are many ways to construct a touch foil. So here we would like to go through some of the typical layers to give you a rough idea of what is possible. It is always your specific project and demands that defines the final design, and so it will be a customized solution that meets your specific requirements. So the components that we need are a substrate to print the electrode on. We need some conductive layers to create the actual electrode. We need some protective layers to protect the conductive layers. And we need a method to connect the touch foil to the PCB. Then we can, as an option, also add graphical layers to create different visual effects in the design. And finally, we need a way to mount the touch foil into the system. So the total thickness of a typical touch sensor, such as the one shown in the picture now, is 200 to 250 microns in the body area, 150 microns in the tail area, and 300 to 350 microns in the connector area, depending on the connector type. So if we go into some of the design considerations for creating a touch foil. So as I said before, we need a substrate, and I would say probably 99% of the touch foils that we produce today are printed on PET foil, but there are also other options such as polycarbonate or other materials. So some of the things that we need to consider when choosing our substrate is, of course, the price, dielectric characteristics, certificates such as UL, for example, for the US market, dimensional stability, the operating temperature range, surface finish, such as should it be glossy, hazy, matte, velvet, or textured. We could have different coatings, such as a print adhesion coating, an anti-Newton coating, anti-static coating, anti-scratch coating, or a UV protection coating. But there are also light characteristics to consider, such as how much light do we need to transmit through the foil, or do we need a diffusing effect? So a couple of takeaways from especially the PET foil is that it's more dimensionally stable than the polycarbonate, it's more chemical resistant, and it works with many of the standard ink systems that is in the market today. We also need the conductive inks to print the electrode, and MegaPrint is currently offering the following 3 types of conductive inks for touch applications. So these are silver, carbon, and PDOT. Silver is typically used for printing traces, in some cases also for printing buttons, and we can even print very thin-lined hatch pattern in the button area to make the buttons, if you need backlighting for the buttons. Carbon is typically used as on the connector points to make it more resistant to abrasion and ensures that silver migration doesn't occur. Carbon can also be used in the button area as a cost-effective way of increasing the electrode area. And finally, PDOT, it's a transparent conductive polymer. It is used for backlit button areas, and it is especially good for backlit button areas where there is a requirement for a high amount of light transmission. We also need some protective layer for the conductive layers, and here we have the option to print a dielectric ink. So the dielectric ink works as so that it prevents oxidation of the silver, for example. It prevents scratches in the conductive layers, and it protects them from electrostatic discharge. So the type of dielectric ink that we can choose can be dependent on what properties that you require, such as do you need a high amount of breakdown voltage, do you need very good bending properties, or do you focus on decreasing yellowing of the ink? We also have other options to, for example, laminate a protective foil instead of printing it, or we can do both. Then I mentioned we can also add graphic inks to create several different features, such as printing symbols. We can print a light blocking layer, and we can create a full covering layer so that you in your assembly line can, for example, laser engrave the symbols yourself. You can also make a light diffusing effect to minimize the hotspots of the LEDs, but this can also be made with a laminated foil. And we can make a so-called dead front effect to make the front panel look as if there's no buttons on the front panel when the system is turned off. And finally, we can also do coloring of the backlit areas with using transparent colors. So in general, for the graphic functionality inks is that it's important to fine-tune the parameters of the color so that it fits your project. So for example, a diffuser or dead front has to match with the type of LEDs that you have chosen, with the distance you have from your LED to your front panel, and which type of front panel have you chosen. So here at MegaPrint, we have the experience and know-how to mix and match a specialized color that fits your project's requirements. For touch foil applications, it's also important to have in mind that the graphic inks that we use should be non-conductive, otherwise they will influence the signal from the touch electrode. The next thing to consider is how do we connect it to our PCB. So the most commonly used method we see is using SIF connectors. So when the product needs to connect to a SIF connector, it requires the product to contain a tail section that is flexible. We also see that when we choose SIF connectors, then the most commonly used pitch is 1 millimeter, but we can also do 0.5. And please be aware that when you choose your SIF connector, to choose the correct type, as some are not designed for printed electronics, as they are designed to scrape into the material. For SIF connectors, it is important that the touch foil has the correct thickness in the area where it connects into the SIF connector. So this is where we are able to add additional thickness to the touch foil in that specific area with something we call a stiffener. And the stiffener can have additional functionality beside adding thickness. It can also add a small handle that you can use to insert your touch foil into your SIF connector. We also see that spring connectors are used. So the advantage here, comparing to SIF connectors, is that we don't need a tail section on the foil, so this reduces the outline complexity. But the disadvantage is that it's not so good for fine pitch designs. Another type we see used is an elastomeric or foam connector, also called zebra connector. So here it has a little bit the same advantage as the spring connector in terms of we don't need a tail section, which again reduces the foil outline complexity. But then it has, on the other hand, the advantage compared to the spring connector that you can have more fine pitch designs. The disadvantage is that you need to have a very uniform compression force, and the foam may harden over time. And finally, we need somehow a way to mount the touch foil into the design. So here we see that 95% of our customers uses a double-sided adhesive as a way to mount the touch foil into their assembly. So using adhesive, then you can relatively easily ensure a stable and repeatable distance from the touch electrode to the user interface. And depending on the adhesive type, you can choose, and your requirement, we can choose between a laminated adhesive or a printed adhesive. So the big advantage of a printed adhesive is that you can have more options in terms of which areas do you want to cover with the adhesive, and which do you not want to cover with adhesive. Some customers prefer not to use adhesive, and in this case, the customer uses a mechanical compression force to keep the foil in its position. The advantage here is that it is easier to repair in case there is ever an issue with the touch foil. We also have the option to laminate foam spacers to the touch foil if needed. The foam can help to take up some of the tolerances in the assembly and ensure, again, a repeatable distance from the touch foil to the user interface. In general, it is important that we have in mind we need to minimize the air gaps in the construction, as this will influence the touch functionality. And so now I would like to go through a couple of examples for you. So here we have a scenario one. So in this scenario, the customer requirements for the touch foil could be like this. So it has to be a low-cost design. The symbol definition of the user interface has to be made on the cover panel. They would like to have room for a status LED in each of the buttons. It has to mount to the light well using a double-sided adhesive. It connects to the PCB using springs, and they would like to have some graphics for their assembly line. So one way to solve this could be as the example shown in the picture now. So here it could be like we could choose a 125 micrometer clear PET foil to minimize the interference with the status LEDs. We can print buttons using a mix of silver and carbon, so printing a silver grid to minimize the, let's say, using the costly silver, but adding carbon to increase the area of the button. The carbon here has the advantage that it covers fully the silver, so there's no need for any dielectrics on the foil. And the silver lowers the resistance of the foil, making it better in terms of the response of the touch foil. The carbon buttons also act as the connection points for the spring connectors. And the button design is could be made with an open area to allow the status LED to shine through. And then we could choose to, because the outline complexity is quite low, we can choose to laminate the double-sided adhesive to the product. And finally, we could add for example, a white graphic print for the assembly line. In a second scenario, the customer requirements could be that the symbol definition of the user interface should be on the touch foil itself. The buttons must be backlit. They want to mount it to a light rail, again using a double-sided adhesive, and they want to connect the touch foil to their PCB using a SIF connector. The solution could look like this. So choosing again a 125 micron clear PET foil to minimize the interference with the backlit symbols. We would have printed traces to the buttons using silver, buttons printed in PDOT, and carbon in the connector area. Then we can add a printed dielectric ink to protect all of the conductive layers. And finally, we can also print a non-conductive black ink to create a symbol definition. Then for the mounting, we could add a double-sided adhesive, again, laminated to the product. And we can add a stiffener so that the connector area matches the thickness specification of the SIF connector that is chosen. And in the third scenario, the customer requirements could look like this. So again, the symbol definition, they would like to have it on the touch foil itself. The buttons are again backlit, but here some foils must be backlit and have a light diffusing and dead front effect. They want to mount it using mechanical compression, and the connecting method is a zebra connector. Here a solution could look like this. So again, using a 125 micron PET foil, printed traces from the connector area to the buttons, printing the button areas with PDOT, and printing carbon in the connector area. And then finally printing a dielectric ink to cover the conductive layers. Then we can add multiple layers of non-conductive inks to create both symbol definition as well as light diffusing effect and dead front effect. So this was 3 examples of touch electrode designs or touch foil designs combining different technologies to create a functional touch foil. And now we'll go to the Q&A section.
Great. Thank you very much, Henrik, for the technical walkthrough. We will go to the Q&A, where we will then try to answer some of the questions that we have. There's a question here. Just get it up here. So I see the QR code on one of the examples. Can you please elaborate a little bit on this? I think Henrik, maybe.
Yeah, so QR code could be used, for example, for your assembly line to let them know which product is this, or which lot number does it come from. It could also be used for serialization code so that you know have a unique identifier for each of the foils.
Yeah. We have one question here. Do you recommend certain ICs for implementing the touch functionality with your foils, especially with regards to resilience of environment influences?
No, in general, we don't recommend the ICs. This is typically chosen by our customer, and then we provide simply the touch foil for your touch application.
So this is something that would normally be outside the scope of what we do.
Yeah, exactly.
Yeah. I have one question here. Two questions in one. Which operating voltage and current can this type of design handle?
So I believe I'm no expert on this, but I believe that the typical voltage that touch foils work under is around 5 volts. But we test them, for example, for insulation on the what do you call it? On the conductive layers for up to 200 or maybe 500 volts to make sure that it's well insulated.
And question number 2 is, how can we obtain a copy of PowerPoint of the slides? Thank you. So I think you will not be receiving the exact slides. You will receive first a link to the presentation or to the webinar, and then a little bit later there will come some kind of marketing material which can then be downloaded. So the slides itself will not be shared immediately after, unfortunately. We have a question here from Philip. Our graphics vary from customer to customer with very low volume for each. If I understood correctly, we could have a basic structure, for example, 3 by 3 buttons from you, and can engrave the individual graphic configuration ourselves on the layer of non-conductive black ink. Is that correct? And if yes, how does this engraving work? Which tools do we need?
Basically, yes, this is correctly understood. So what we see some of our customers use is laser engraving systems. Which exact systems that you need, I can't help you with. We can, of course, refer to some of the, or we can refer to a manufacturer of laser systems that can help you choosing the right machine.
Yeah. But it is correct. It is a way of creating the different variances. So if you have different visuals for different customers, but if you can use the same, you can say the conductive side of the foil, this is a very good way of creating the different variants. So it is definitely something that we see being very relevant in many cases. Then we have a question here. Good morning. What distance to the sensor can we achieve? And is the sensor customizable, e.g. with printed plastic plates?
So I would say the typical distance that we see used is between 1 and 4 millimeters from the sensor to the outside of the front panel. So typically the sensor is put directly up on towards the front panel, and then you have a thickness of the front panel between these 1 to 4 millimeters.
Okay, and is the sensor customizable, e.g. with printed plastic plates?
Yeah, I'm not really sure I fully understand the question, to be honest. So maybe we can answer you later on this one.
Yeah, let's do so. That's a question here. What is the real printed line width for the silver in the touch area? Thanks.
So I assume that you mean in the area where you have a backlit button. So where I was talking about a very thin line head pattern. So here we can print down to 50 micron lines, whereas the traces are typically made with a 300 micron width or 200 micron width.
Yeah, so the traces normally when we use fine line silver is has a nominal value of 50 micrometers in thickness, and then with an air gap in between.
Yeah, in width, yeah.
Yeah. Okay. Good. So I can see we have a question here. Sorry, we have a question about the price of the foil that we saw in the demo. So I think prices always vary with the number of layers and processes for lamination and testing and so on that needs to be done. So instead of giving a price estimate based on a sample, then I would rather go into a specific discussion separately to know more about the needs, and then we can estimate a budget price based on that. So. Which kind of connectors do you use for Zebra?
So if you're talking about the foam connector itself, then this is again one of the areas where we typically we're not the expert on this area. So we provide again the touch foil that fits with the Zebra connector that you have chosen. But the Zebra connector itself, you should talk with your supplier of those.
Yes.
In terms of which ones you need.
So normally we align on what kind of connector is needed, normally specified by the customer, and then we help to customize the layout of the sensor in a way that it fits perfectly with the sensor type that is chosen. But the actual sensor is normally specified and chosen by the customers. Just checking if I missed any questions here. I think we have more or less answered all of the questions right now from the list. But if anything pops up later on, then you have our contact information from the slides, and you are always welcome to reach if you have anything you think we can be. So I think we'll just finish off here, and thank you everybody for joining in and for your interest in this this area. Yeah, have a great rest of the day.
Yeah.
Bye for now.
Thank you. Bye.